Consider the absolute destructive potential of a single naval shell.
A solid mass of forged steel and high explosives weighing in at precisely 2,700 pounds.
Now envision this immense projectile forced through a rifled steel barrel measuring 66 feet in length,
Accelerating under violent pressure to achieve a muzzle velocity of 2,500 feet per second, well beyond the speed of sound.
Traveling a distance of 24 miles downrange to gouge an impact crater 50 feet wide and 20 feet deep. It is critical to recognize that this is not a modern guided missile. This is a conventional gun. What follows is a precise analysis of the brute force military engineering behind the Iowa Class Battleship's 16-inch Mark 7 naval gun.
The Mark 7 was engineered in the late 1930s for one uncompromising tactical objective: to outrange and outpenetrate the Imperial Japanese Navy's Yamato Class Battleship. The intent was to deliver a lethal blow before the enemy vessel could even return fire. Every dimension of this weapon was mathematically dictated by this singular goal.
To understand such extreme range, we must establish its foundational engineering variable. In large-scale naval terminology, 50 caliber does not refer to the diameter of the projectile. It refers to the ratio of barrel length to bore diameter. 50 multiplied by 16 inches results in a massive barrel length of 66.7 feet. This dimension strictly dictates the governing physics of the weapon's power.
Pillar 1. Internal ballistics and propellant physics. The engineering behind this operation rests on 3 pillars, beginning with the extreme high-pressure physics contained entirely inside the gun chamber.
The firing sequence relies on rapid controlled combustion. First, 6 silk bags holding 660 pounds of smokeless propellant are loaded directly behind the shell. Next, the heavy steel breech is locked, and the charge is electrically ignited. This simultaneous combustion generates a tremendous volume of high-pressure gas possessing only one possible direction to expand. Finally, this rapidly expanding gas relentlessly forces the 2,700-pound projectile forward. The internal mechanics are mathematically exact. Gas pressure multiplied by the bore's cross-sectional area equals force. The 66.7-foot barrel is critical here. It allows this extreme acceleration to continue just long enough to extract maximum velocity before the internal gas pressure dissipates. The result is a sustained forward thrust, producing an exit speed of roughly 1,700 miles per hour.
Pillar 2. External ballistics in flight. We must now analyze the environment the moment the projectile leaves the muzzle. The shell immediately begins a 90-second flight path toward a target 24 miles away. To achieve this absolute maximum range, the barrel is elevated to 45 degrees, sending the massive shell to an apex altitude of 33,000 feet. Throughout this high parabolic arc, 4 precise forces act upon the shell simultaneously: forward momentum, carrying it downrange; gravity, pulling it downward at 32 feet per second squared; aerodynamic drag, continuously decelerating its mass; and the Coriolis effect, deflecting the shell laterally as the Earth literally rotates beneath its flight path.
Hitting a moving target at a distance of 24 miles requires calculating every atmospheric and flight variable simultaneously. The Iowa class utilized advanced analog radar-guided fire control computers capable of generating a precise firing solution in zero visibility. The Yamato, by contrast, relied on optical rangefinders, systems that failed entirely in adverse weather or heavy battle smoke. This deliberate engineering superiority meant the Mark 7 could engage accurately while the enemy was entirely blinded.
Pillar 3. Terminal penetration engineering. This final phase dictates the catastrophic mechanical destruction caused by the shell upon arrival.
The Mark 8 super heavy armor-piercing shell utilizes a hardened steel tip engineered specifically to maintain structural integrity through the massive shock of impact. At a range of 11 miles, this shell possessed the kinetic energy required to punch through 20 inches of hardened steel armor. The Yamato's heaviest belt armor was 16 inches thick. Therefore, the gun built to destroy the Yamato was engineered with a lethal, calculated 4-inch margin over the enemy's maximum defense.
The bunker-busting irony. This brings us to a profound tactical reality. Despite its lethal capability against enemy armor, the Mark 7 gun never fulfilled its intended surface engagement purpose.
The weapon's operational timeline reveals a stark truth. It never fired at an enemy battleship.
Engineered in 1938 specifically to destroy the Yamato, it was permanently deprived of that duel when the Japanese flagship was sunk by carrier aircraft in April 1945. Yet the Mark VII remained active for decades, firing its final combat rounds in 1991 against Iraqi targets during the Gulf War.
The weapon spent 47 years in operational service, spanning multiple modern conflicts. It fired its massive payloads exclusively at land targets, never at enemy ships.
This operational shift resulted in a highly effective unintended engineering consequence. The 2,700-pound armor-piercing shell, painstakingly designed to defeat 16 inches of battleship steel, accidentally became the most effective bunker-busting weapon in the United States arsenal. Upon impact, the sheer kinetic energy of the Mark VIII shell proved capable of penetrating 21 feet of solid, reinforced concrete. The ultimate battleship killer seamlessly transitioned into the ultimate siege weapon.
The most powerful naval gun America ever built outlasted the threat it was designed to destroy and outlived the era it was designed to define. That is not irony. That is engineering outlasting its own purpose. But as modern warfare shifts entirely to hypersonic missiles, automated drones, and digital targeting, we are left with a final question. Will the world ever again see a weapon where sheer, brute force mechanical engineering so thoroughly dominates the battlefield?